That's what I'm talking about. This means something to me, man.
Hi everyone, welcome back to Surviving Math with Chan. You're here with Chani Harris, and today we'll be looking at tonight. We'll be looking at mathematical induction. So I know that this topic is one that many people view as difficult, which is why I'm doing a video on it. After this video, I want you guys to realize that this topic is light work, no reaction. Because you know why? You know why, guys? Because you watched this video to the end. So one thing we should note is that mathematical induction is based off the idea of inductive reasoning. And with inductive reasoning, we're just taking a specific argument and we're trying to make some general conclusion. So for example, Tommy likes KFC. Tommy is a Jamaican. All Jamaicans like KFC. So we realize that we're taking Tommy, we're being specific to one person, and we're making a general conclusion where we're basically saying all Jamaicans. Since Tommy is a Jamaican and he likes KFC, all Jamaicans like KFC. So that's the whole idea with inductive reasoning. We're taking a specific argument. We're basically using specific premises in order to make some general conclusion. So there's two main scenarios where you'd use mathematical induction to prove an argument is true. And our first scenario is where we have a formula and we want to show that the formula works for some series. So for example, we'll have this series 1 plus 2 plus 3 plus ... plus n. N is the last term of the series and it is a natural number. If you realize, the series is basically consecutive natural numbers because we have our first natural number being 1. After 1 comes 2, after 2 comes 3, and etc. Right? All the way down to some last term, some last natural number. Right? All we're saying is that we can take the last term of the series and substitute it into the formula to get the sum of the numbers. So imagine, what if that last term was 6? We want to find the sum of 1, 2, 3, 4, 5, 6. We're saying that once we substitute 6 into this, where we'd have 6 in brackets 6 plus 1 or all over 2, we would get the sum of those numbers. With mathematical induction, we want to prove that this is true for every number. So we're not just taking one natural number. We want to show that this formula works for whatever natural number will stop the series at. Next is we're trying to prove that an expression is divisible by some term. So for example, we have the expression 5 raised to the n minus 1 is divisible by 4. Using mathematical induction, we can basically show that this is true for every n that is a part of natural numbers. So whatever natural number we substitute into this should be divisible by 4. So I meant to say that the natural number that you substitute into the expression should make the expression a number divisible by 4. And we can prove that using mathematical induction. So there's 3 steps involved in proving that a statement is true using induction. And our first step is the base case. So this is where we're showing that the statement is true for the first case. So usually it's n equal 1. However, it doesn't always have to be n equal 1. It all depends on what the statement says. So for example, if we're to consider the second scenario where we have an expression and we want to show that that expression is divisible by some number, right? What if that statement was to say that this is true for every n that is an even number starting from 2? Since the statement specifically said that it's true for every even number and we're starting from 2, 2 would be our first case. Therefore, we would have to use n equal 2 as our base case. So that's just an example to show that it's not always going to be n equal 1 in all cases. You have to pay attention to what the statement says. But yeah, our next step is the assumption case. So this is where we're assuming that it is true for some large number k. So k is our variable, k is some large number, and we're saying that n is equal to k. So with this case, all we're doing is that we're substituting n for k, basically. We're putting k in whatever expression, formula, and we're assuming that is true. That's all we're doing. And our final step, the third step, is the implication case. So this is where we're using our assumption to show that it's true for n equal k plus 1. So what we'll have from the assumption, we're going to take that, since we assume that it's true, we're going to take it and we're going to show that it's true for n equal k plus 1. And by doing that, we can make our general conclusion. Before we get into the examples involving this first scenario, let's have an understanding of how to represent a series in sigma notation. So right here, we'll have our sigma notation, basically. And in the middle, you'll notice that we'll have our formula. So this is where we would have our formula. At the bottom, we would have the lower limit. So that's basically what we're starting with. What's the first value of I that would substitute in the formula, and then at the top we would have our upper limit, so that would be the last value we would substitute into the formula. And this is basically representing the phrase that the sum of ai as I goes from 1 to n. So that's what we have for the sigma notation. And you're gonna understand how this is important when we get into the examples. So here's our first example. We want to prove the statement using induction. So we have the series 1 plus 2 plus 3 ... plus n is equal to n times, in brackets, n plus 1, and this is all over 2. And we're seeing that this statement is true for every n that is a natural number, because we have the big N basically denoting a set of natural numbers where n is greater than or equal to 1. So the first thing I'm going to do is that I'm going to rewrite my left-hand side. So let me actually highlight that. This is our left-hand side of the statement, basically, and this is our right-hand side. And I want to rewrite my left-hand side, the series, in terms of sigma notation. So that's what we just discussed. So I'm going to have my symbol. So in the middle, recall that we would have the formula. So the formula is, when I say the formula, I mean what's on the left-hand side. Remember that we're dealing with the left-hand side. And the formula would simply be the expression that we would see at the end, but would replace it with a different variable. So just like how we have n right here, we'd use a different variable to basically represent the formula. So instead of saying n, let's have a variable I, for example. We could use any letter variable like I, J, P, yeah. So after identifying what is our formula, let's identify what is the lower limit. So this is the first value that we would substitute in the formula. So just like we'll have I, we'll have to look on the left-hand side, we'll have to look what is the first term of the series, basically, because that's the first number that we would basically substitute into the formula. So we would have I, the first term of the series is 1. That means that would be the lower limit. So I have I is equal to 1, and then we'll have to identify our upper limit, and that would be the last term we would substitute in the formula in order to find the sum. So the last term right here from the left hand side, we notice that it's n, so that's what we're going to put right here. So this expression would be the same thing as saying the sum of I as I goes from 1 to n. And the other thing, we'll have our left hand side, let's just rewrite our right hand side. So we'll have n in bracket n plus 1 over 2. And that's it in sigma notation. So now let's actually move on to proving that the statement is true. And our first step is the base case. So with the base case, recall that we're showing that it's true for the first case. And from here, you notice that we have our statement. So this is our left-hand side. We'll have the series being equal to this formula. So we're saying that we can use this formula to find the sum of the terms of this series, right? At the end, if you notice, we'll have for every n that is a part of a set of natural numbers where n is greater than or equal to 1. That part of the statement is telling us what is our first case, basically. We're saying that from 1 and onwards, the statement is true. So the statement is true where n is equal to 1, 2, 3, 4, 5, 6. We're starting from 1. Because we're starting from 1, that's our base case. And that's what we'd have to show is true. So our base case would be where n is equal to 1, because 1 is our starting point. So now that we have that, all we're going to do, wherever we say n, we're going to put 1. So we're going to have our left-hand side, the symbol. So we say n at the top. So where we say n, we're going to put 1. And then have our formula and our lower limit. And then we move on to the right-hand side. So here we have on the right-hand side, we have n. So remember, wherever we say n, we're going to put 1. So 1 in bracket 1 plus 1 all over 2. Right. So from the left-hand side, remember that in the middle is our formula. So it's like we're substituting 1 into our formula, because down here is like it's telling us where we're starting from. We're starting from 1, and this up here is telling us that we're ending at 1. So we're going to substitute 1 into the formula and then leave it at that. So when we substitute 1 in I, we're saying that I is equal to 1. Since I is equal to 1, on the left hand side we'd simply have 1. Next thing, on the right hand side, we'll have 1 being multiplied by 1 plus 1. 1 plus 1 is 2, and that would be over 2. So 2 divided by 2 is 1. Therefore, we see that the left-hand side is equal to the right-hand side. And because that's the case, that means that this is true for the base case. So it's true for when n is equal to 1. So we can make that note true. Yeah, this is Sterling, okay. For n equal 1. So after doing our base case, we'll move on to our second step. And that's the assumption step, the assumption case. And with the assumption case, all we're saying is that n is equal to k. We're assuming that it's true for when n is equal to k, and k is just some large number. So from here, it's like if we're to like go back to this representation of the series, it's like we're saying 1 plus 2 plus 3 plus dot 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 plus k. And that would be equal to whatever we have on the right hand side. And all we're saying is that wherever we say n, we're going to put k in this case. So on the right hand side, we would have k, because that's where n is, in bracket k plus 1 over 2. Because wherever we say n, we're putting k in this case. And I'm going to rewrite this in sigma notation. So remember, wherever I say n, I'm going to put k. We say n at the top. Therefore, remember that n is equal to k. Therefore, we're going to put k at the top. Then have our formula, then have our lower limit. And that would be equal to k in bracket k plus 1 all over 2. And that's our assumption case. We're just assuming that this is true. And now we have our final step, and that's the implication case. So recall, in this case, all we're doing is that we're taking our assumption in order to show that the statement is true for n is equal to k plus 1. So with this, what we're going to do, we're going to do the same thing that we have been doing. So we're going to replace whatever we say n, we're going to put k plus 1. So we'll have our sigma notation right here. Where I say n, I'm going to have k plus 1. Have our formula, have our lower limit. And this would be equal to the right hand side. Wherever I say n, I put in k plus 1. So I'm going to have k plus 1. Recall that k plus 1 is an expression, so you have to put it in brackets. So k plus 1, then you're going to have in bracket k plus 1 close bracket, all over 2. So that's our right hand side. And if you notice, if we're supposed to use our assumption, which we're going to do, we'll have to use our assumption in this case, we can see that since this statement, this representation right here is basically telling us that we're trying to find the sum of numbers from 1 to k plus 1. So it's like we're saying we're going from 1 plus 2 plus 3 all the way down to k plus 1. So that is what this means basically. And since we know that all the way from like 1 all the way down to k is this, which is equal to this, we can replace it in our representation. So instead of like having this, we could say that we can use our summation of terms from 1 to k, have our symbol, we're taking this, and we can simply just add our last term right here, k plus 1, and that would be the same thing as saying this, because at the end of the day it's the sum of numbers from 1 to k plus 1. And since we know the sum of numbers from 1 to k, if we simply add k plus 1, it's the same thing. And this would be equal to our right hand side. So I'm going to rewrite that. And I can simplify this. Since I have k plus 1, that would simply be k plus 2. So that's what I'm going to write, k plus 2 in that bracket, all over 2. Oh, and I should have this in bracket. Yeah, make sure you have the bracket over this when you're adding a term to it. Another thing, since this is equal to what we have right here, I can replace this representation with what we have on the right hand side right here, the k times k plus 1 all over 2. And that is what I'm going to do. So before I erase this, I just want to make it clear that since this is equal to this, if you can see, yeah, since this is equal to this, I can replace this representation with the formula that we have right here. And we're saying that this, or left hand side, is equal to this. So now that we have this on our left hand side and this on our right hand side, all we're doing now is that we want to show that both sides are equal. So we want to rewrite this in terms of this. We're trying to get this in a form where it looks like this. Exactly like that. Yeah. And what I'm going to do is that since I have a fraction right here, I can find the lowest common multiple, and that would be 2. And yeah, I'm gonna use this method. So I'm gonna have 1 into 2, 2, and we're gonna times 2 by our numerator, and then 2 into 2 would give us 1, so we're just gonna have the same numerator right here, and that's what we're gonna have. I'm gonna rewrite our right hand side over 2. So we have k, and then in bracket k plus 1, plus 2, and then in bracket k plus 1. So what does these two expressions have in common? K plus 1. Since they have k plus 1 in common, that makes k plus 1 a factor. And all we're going to do with the factor is that we're going to factor it out, because it's a common term among the two expressions right there. It's a common term among k times k plus 1 and 2 times k plus 1. So we're going to factor out our k plus 1. And when we factor k plus 1, on here, right here, we're going to be left with k. And then here, we're just going to be left with 2. So we're going to have our plus 2, of course. And that would be over 2. And this would be equal to our right hand side. All over 2. So if you notice right here, we'll have k plus 1 times k plus 1, meant to say k plus 2, all over 2 on our left hand side, and that's the exact same thing we have on our right hand side. Therefore, the left hand side is equal to the right hand side, and that we basically showed how it's true for how the argument is true, how the statement is true for n is equal to k plus 1. So we can just make a general note that it's therefore true for n equal k plus 1. And if you think about it, since we showed that the statement is true for n is equal to 1, and for the first case, basically, n is equal to k, some random large number, and then the statement is true for the number after k being k plus 1, n is equal to k plus 1, we can make a general conclusion to say that the statement is true for where n is equal to any natural number from 1 onwards. So that's the general conclusion we can make, and that's how we prove with induction. So here's our second example. We'll have 1 plus 4 plus 7 plus ... plus in bracket 3n minus 2 is equal to n in bracket 3n minus 1 all over 2. And this is for every n that is a natural number where n is greater than or equal to 1. So before we get into proving, let's actually rewrite our left-hand side, the series, the terms being added, in sigma notation. So with sigma notation, recall that in the middle we would have our formula. With the formula, remember that you're focusing on the left-hand side. And with the formula, you're looking at the expression at the end. This is our expression at the end, the 3n minus 2. With this expression, you're going to take a different variable for n. So just like how we have 3n minus 2, we're going to take some other variable, for example, I, j, p, whatever the variable might be, and we're going to just put it there and write our formula. So we're going to have, let's say, 3j minus 2. And that's our formula, and that's where we would put it, in the middle. Next, we want to know our starting term. So what's the first term we're going to substitute in this formula? And the first term is simply just the first term of the series that we have right here. And our first term is 1. 1 is the number that we're starting with. 1 is the number that starts the series. So that would be our first term, being right here. That would be our lower limit. So we're going to say that j is equal to 1. And with the upper limit, which is at the top, we're looking at what term you're ending with. So what is the last term you're going to substitute in the formula? So if you look at the n, you realize that in the expression, you basically substituted n right here. N is basically being the last term being substituted in this expression. Because if you think about it, we could put n right here, and we're going to have 3n minus 2. Because that's the last term of the series. And so remember that this representation is the same thing as saying 3j minus 2 as the j, or variable, goes from 1 to n. So 1 is the first number you're going to substitute in the formula, and then n is going to be the last number you're going to substitute. So if you're to actually think about it, you're just substituting 1 being our first number. So 3 times 1 minus 2, and you get that. You then move on to your other value. What's the number after 1? The number after 1 is 2. So you're just going from 1 all the way to some number n. So 3 times 2 minus 2. So if I was supposed to calculate this, you're going to get 1. If you're supposed to calculate this, 3 times 2, 6. 6 minus 2 would give us 4, or second term. Next, you move on to 3. 3 times 3 is 9. 9 minus 2 is 7. You realize that you're getting the same thing. So that's what we're saying. After we have our sigma notation done, we're just going to rewrite our right hand side. So n times 3n minus 1 all over 2. And yeah, now let's get into proving. Our first step is the base case. This is where we're showing that it's true for the first case. So let's identify our first case. From what we have right here, we're saying that this is true from when n is greater than or equal to 1. 1 is our first case, basically, because we're starting from 1. That's the first value that makes the statement true. So we're gonna have our base case. And this is where n is equal to 1. And all we're going to do right here, remember, wherever we say n, we're going to put 1 in the base case. So we see n at the top, we're going to put 1 there. And then have our formula, then have j equal 1. After we have that, let's just work with the left-hand side first. We're going to just substitute 1 into the expression, the formula right there. I'm going to have 3 in bracket 1 minus 2. So 3 times 1, 3 minus 2, 1. And that's our left hand side. So now we're going to move on to the right hand side. And all we're going to do, we're both to n, we're going to put 1. So we'll say n. So n, so we're going to put 1. Then we'll have 3n, so it's 3 times 1 minus 1, close bracket, all over 2. This would be equal to 1. And then we'll have 3 times 1 is 3. 3 times 1 is 3, minus 1, all over 2. Then we'll have 3 minus 1. That would give us 2. And therefore, we'll have 2 over 2. And 2 over 2 is simply 1. So we'll have our left-hand side being 1 and our right-hand side being 1. So 1 is equal to 1. Therefore, our left-hand side is equal to our right-hand side. And because the left-hand side is equal to the right-hand side, the statement is true for the base case. So now we move on to the second step, and that's the assumption case. So we're assuming that the statement is true when n is equal to k. So wherever we say n, we're going to put k. So on the left-hand side, we see n as the upper limit. So we're going to replace it with k. So we have k, then have our formula. And yeah. And if we're supposed to find the k term, that's a part of this series, we would have to use the formula right here to find it. So we're just substituting k into this formula, and the term would simply give us 3k minus 1. Not minus 1, minus 2. And just for me to make it clear, this would be the same thing as saying 1 plus 4 plus 7 plus ... plus 3k minus 2. So this is from 1 all the way to our k term. The sum of numbers from 1 all the way to the k term using this formula. Next, this is our left hand side, by the way. So now we'll move on to our right hand side. So let me just put it right here, right hand side. So all we're doing, we're substituting k into this expression that we have right here. So we'll have n in bracket 3n minus 1 all over 2. So we're gonna have k in bracket 3k minus 1 all over 2. And I can choose to basically multiply k by what's in the brackets. So I'm gonna have 3k squared minus k all over 2. And that's what we have on the right hand side. And our final step is the implication case. So we're basically showing that it's true for n, the statement is true for n is equal to k plus 1 using our assumption. So we're just gonna do this first. Wherever we say n, we're gonna put k plus 1 in this case. So k plus 1 becomes our upper limit. We would have our formula and have j equal 1. And this would be equal to what's on the right hand side. We're replacing n with k plus 1. So we're gonna have in bracket k plus 1, then have that big bracket 3 times k plus 1, where we say n, we're putting k plus 1, minus 1. And this is all over 2. So if we're supposed to take this and represent it in using our assumption case, using our assumption, since our assumption is basically telling us the sum of terms from 1 all the way to our k term being the 3k minus 2, what we can do is that we want to find what is our k plus 1 term using our formula first. So just like how we found the k term using the formula, we're going to do that for our k plus 1 term. So let me just make a side note. So we'll have 3j minus 2. So where we see j, we're going to put k plus 1. And this would give us, so we'll have 3k plus 1 minus 2. So 3k plus 3 minus 2. And that would be 3k minus plus 1. I'm sorry. 3k plus 1. So that would become our k plus 1 term. So we're going to take our assumption. Since this represents the sum of terms from 1 all the way to our k term, we're going to just have that there. And since we want the sum of terms from 1 all the way down to k plus 1 or k plus 1 term, and this is our k plus 1 term. All we're going to do is that we're going to add the 3k plus 1. And that would be equal to our right hand side. So I'm going to simplify this. So when I simplify this, I'm going to have, okay, we'll have 3k, 3, and then in bracket k plus 1. So 3 times k would give us 3k. Then 3 times 1 would give us 1. So I'm going to have plus 3. Wait, 3 times 1 would give us 3. So I'm going to have plus 3. And then I'm going to have the minus 1. 3 minus 1 would give us 2. So I can just replace that with 2. And this would be all over 2. So that's our left hand side being equal to our right hand side. And from our assumption again, we notice that since this is equal to what we have on the right hand side, the 3k squared minus k all over 2, we can simply replace this, what we have right here, with the 3k squared minus k all over 2. Just put it right here. And I'm going to give myself space for that. So this is what we have. So remember that I said that we're replacing this with what's on the right hand side over here from our assumption. So replaced it with this. Yeah. And then we're saying that this, the left hand side, is equal to the right hand side. So all we have to do is show this in terms of this. Basically, we're showing that it's equal, so we're going to write it the same way. So from here, I'm going to find LCM, because it's a fraction right here. So the LCM is 2. So 2 into 2 would give me 1. So that means I can just write back the numerator. Plus 1 into 2 gives me 2. So I'm going to have the numerator being multiplied, the numerator right here being multiplied by 2. So I'm going to have 2 times the 3k plus 1. And this would be equal to our right hand side. So let's just keep that there, because we're trying to get it into this form. Yeah. And yeah, that's what we have so far. So what I'm going to do, since we have a 2 being multiplied by what's in the brackets, I'm going to just expand that. It's being factorized, so I'm going to expand it. So I'm going to have 3k squared minus k plus 3 times 3k would give me 6k. And 2 times 1 would give me 2. And this would be over 2. And we're saying that this would be equal to what's on the right hand side. Okay, we have 3k squared minus k plus 6x plus 2. So we have like terms being right here, the minus k and the 6k. So I'm going to just simplify that to get 3k squared plus 5k plus 2 over 2, because minus k plus 6k is the same thing as 5k. It's like saying 6k minus k, 5k. And that would be equal to our right hand side. So if you notice on our left hand side, we have a quadratic being in our numerator. So since, if you notice, we have this is basically saying that these are the factors of the quadratic. However, we have to prove that. We have to show it. So we're going to factorize the quadratic. So this is basically what we have. And I'm just going to take the numerator, the quadratic, and factorize it separately. So I'm taking the 3 squared plus 5x plus 2. And I'm going to factorize this. So I'm using the AC method. So we're looking at the 3 and the 2. We're going to multiply it. When we multiply it, we get a positive 6, right? And all we're doing is that we're trying to find two numbers that when we multiply them, we're going to get the positive 6. And when we add them together, we're going to get the middle term being the 5. Yeah. And those two numbers would be 3 and 2. So positive 3 and positive 2. So we're going to have 3 k squared plus 3k plus 2k plus 2. Now I'm going to group terms and I'm going to factorize. So I'll have 3k squared plus 3k. The common factors there would be 3k. and we're left with k plus 1. On this side, we're going to have k plus 1. I'm going to factor out 2. Therefore, we're left with k plus 1 as a common factor, and we would have 3k plus 2. So I'm going to replace the numerator, the quadratic that I have right here, the expression, as this, the factorized version. So I replaced it with the factorized version. So if you notice, we'll have a k plus 1 times 3k plus 2 all over 2, and that's the same thing we'll have on the right hand side. Therefore, the left hand side is equal to the right hand side. And since the left hand side is equal to the right hand side, we can see that the statement is true when n is equal to k plus 1. The statement is true for n is equal to 1, the first case, n is equal to k, some large number, and n is equal to k plus 1, the number right after k, basically. We can say that, we can make a general conclusion to say that this statement is true for every n, where every n is a natural number. Every n is a natural number, and it's greater than or equal to 1. And here we have our third example. So we have 1 plus 2 plus 2 squared plus dot 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 plus 2 raised to the n minus 1 is equal to 2 raised to the n minus 1. And this is for every n that is a natural number where n is greater than or equal to 1. Our first step is to rewrite the left hand side in sigma notation. So we have that. And what we're doing, our formula, we're going to look right here. We see 2 raised to the n minus 1. All we're going to do, we're going to take some variable to replace the n that's right there. So let's say we want to use the variable q. So we're going to have 2 raised to the q minus 1. And that's our formula. Our lower limit would be q equal 1, because that's the first term that we're starting with, our starting term. That's our lower limit. And then our upper limit would be n, because that's the last term that we're substituting in the formula, if you notice. That's our left hand side. And that would be equal to our right hand side being 2 raised to the n, and that's subtracted by 1. Next is our base case. So this is where we're showing that it's true for our first case. In this situation, it would be, our first case would be 1, because that's what we have. We have n is greater than or equal to 1. So that's what we're going to have first. That's our first case, so that's what we have to show. That's what we have to show is true. So base case, I'm going to have n is equal to 1. Therefore, whatever we say n, we're going to put 1. So 1 at the top. We have our formula, and that's our left hand side. And I'm just happy right there, left hand side. And then for our right hand side, we're substituting 1 into this. So we're gonna have 2 raised to the first power, and then we'll have subtract 1. So with the left hand side, all we're doing is that we're substituting 1 in our formula right here. So we're gonna have 2 raised to the 1 minus 1, and that would simply be 2 raised to the 0. Any number raised to the 0 power would give us 1. And then for our right hand side, we'll have 2 raised to the first power, and then we're subtracting by 1. So we'd have 2 raised to the first power would be 2, so that's what we have. And then we're subtracting by 1, and that would give us 1. So from here, we can conclude that the left hand side is equal to the right hand side. And because the left hand side is equal to the right hand side, it's therefore true, the statement is true when n is equal to 1, the first case. So true for n equal 1. Next, we move on to the second step, and that's the assumption case, where we're assuming that the statement is true for n is equal to k. So wherever we say n, we're going to put k. So we're going to have k. Then we have a 2, our formula. Yeah, so 2 raised to the q minus 1. So q equal 1. That's our left hand side. And from here, we're gonna find what is our kth term. Yeah, kth term. And all we do to get that is that we're substituting k into our formula right here. So from here, our kth term is simply 2 raised to the k minus 1. Next, we're gonna move on to our right hand side. So we're above the n, we're gonna put k. So we're gonna have 2. So 2 is raised to the n, so we're gonna have k right here minus 1. And yeah, that's it. We're assuming that that's true. And we move on to our final step, being the implication step. So notice how I have the assumption at the side. And recall that this representation is the same thing as saying 1 plus 2 plus 2 squared plus dot 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 plus our kth term that we just found right here. And our kth term is 2 raised to the k minus 1. So that's the same thing. With the implication, we're above the n, we're going to put k plus 1. So we're going to have this, we're going to have k plus 1 at the top, and then 2 raised to the k minus, 2 raised to the q minus 1, our formula. Yeah. And this is equal to our right hand side being, oh, I rewrote this wrong. I'm sorry, guys. My bad. And this is equal to our right hand side being 2 raised to the k plus 1, because that's where we say n, and that's subtracted by 1. So from our formula right here, just like how we found the kth term, we can find the k plus 1th term. And what we're doing is that we're substituting k plus 1 where we say q. So we're going to have 2 raised to the k plus 1, and then we're going to have minus 1. 1 minus 1 leaves us with 0, so we're going to simply have k 2 raised to the k as our k plus 1 term. So I'm going to make a side note of that. So k plus 1 term is 2 raised to the k. So next, recall that with our assumption, we can use the assumption to show this. So since, as I said before, since this is showing the sum of terms from 1 all the way to the kth term, we can just simply use this and just add or k plus 1 term, because it's the same thing. Yeah, so I'm gonna have our assumption plus our k plus 1th term, and that would be equal to our right hand side. And from here, since we know that this is equal to this, so this is equal to this, we can just replace it. So right here where we have this representation, we can replace it with 2 raised to the k minus 1, and then I'm going to have my k plus 1 term being 2 raised to the k, and that would be equal to 2 raised to the k plus 1, and then I have minus 1. And from here, all we want to do is show that the left hand side is equal to the right hand side. So here we have it. We have 2 raised to the k minus 1 plus 2 raised to the k is equal to 2 raised to the k plus 1, and that's being subtracted by 1. So from here, you're going to notice that we have this term right here, where we have 2 is being raised to k plus 1. And if you're familiar with indices law, you should know that 2 raised to the k plus 1 is the same thing as saying 2 raised to the k times 2 raised to the first power, 2 raised to the 1. And that's what we're going to write it as. And you know, 2 raised to the 1 is simply 2. So from here, what we want to do is that we want to take some variable in order for it to represent 2 raised to the k, so we can work with the equation better. So we want to get the two sides to look the same. So I'm going to take a variable h, and I'm going to let it be equal to 2 raised to the k. And from that, wherever I say 2 raised to the k in this expression, this equation, I'm going to put h. So h minus 1 plus h equal h times 2 minus 1. And from here, I have h plus h. That's going to give me 2h. And then I have minus 1. I have h times 2. That's going to give me 2h. And then I have minus 1. You realize both sides will have 2h minus 1. And we'll have 2h minus 1. The left-hand side and the right-hand side are the same. So I'm going to replace back the h with the 2 raised to the k. Okay, 2 raised to the k minus 1. And we're saying that the left-hand side is equal to right-hand side. And since the left-hand side is equal to the right-hand side, that therefore means that the statement is true when n is equal to k plus 1. And since the statement is true for n is equal to 1, n is equal to k, and n is equal to k plus 1, we therefore prove that we can make a general conclusion to say that the statement is true for every n that is a natural number where n is greater than or equal to 1. So we're moving on to our second scenario where we're trying to prove that an expression is divisible by some number, some term. So with this, let's just establish what divisibility means, because this is really important. So basically, when a number is divisible by some term, we can say that that number can be written as the term multiplied by some integer. So for example, if we were to say that, 4 is divisible by 2, we know that 4 is divisible by 2 because we can write 4 as 2 times 2, and 2 is an integer. So just like how we have it right here, we have 4 is equal to 2 times 2, and 2 is an integer. And the same situation would go for a number like, let's say 15. So 15 is divisible by 3. Why? Because 15 can be written as 3 times 5, and 5 is an integer. So that means that 15 is divisible by 3. So let's just establish that. You're going to see how this is really important for us to move forward with the examples. So here's the first example we're going to do. So we'll have 6 raised to the n minus 1 is divisible by 5. And this is where n is greater than or equal to 1. And with this, the same steps apply. We would have to do the base case, then we move on to the assumption case, and then we do the implication case. So we're starting with the base case. So we'll have to show that it's true for the first case. So we're saying that this statement is true where n is greater than or equal to 1. Since we're saying that n is basically like equal to 1, that's our first value where the statement would be true for. That's where we'd have to show that the statement is true for n is equal to 1, because 1 is our first case. So we're going to have base case, base, and have n equal 1. Next, all we're going to do is that right here, we're going to substitute where we see n, we're going to put 1. So we're going to substitute for 1. So we're going to have 6 raised to the 1, because that's where n is, minus 1. Right? And then we're going to be left with 6 raised to the first power is 6. Okay, then we subtract by 1. So 6 minus 6 is 5. Now the question we have to ask is 5 divisible by 5? Yeah. Why? Because we can write 5 as 5 times 1, and we know that 1 is an integer. So that's our base case. So now we move on to our assumption case. So we're assuming that the statement is true where n is equal to k. Where was the n? We're going to put k. So we'll have a 6 raised to the n minus 1. Therefore, we're going to have 6 raised to the k minus 1. And since we're saying that this expression, since we're assuming that this expression is divisible by 5, recall that I said that once an expression or a number is divisible by 5, you can write it as 5 times an integer. Therefore, we're going to write this. This is going to be equal to 5 times some variable. We're going to have some variable representing our integer. And let's call that variable p. So let's just highlight that p is an integer. It's a part of that set of integers. and that's our assumption. So from here, we're moving on to our final step, and that's the implication case, where we're showing that the statement is true where n is equal to k plus 1 using our assumption. So wherever we say n, we're going to put k plus 1. That's the first thing we're going to do. And from here, you notice that we have 6 raised to the k plus 1. This can be written as 6 raised to the k times 6 raised to the 1, and then we would have the minus 1. So with the implication case, recall that you're trying to find a way to include the assumption case. So if you notice, we'll have 6 raised to the k. This mark is done. We'll have 6 raised to the k. In our assumption, we'll also have 6 raised to the k. So what we can do is that we can probably write our assumption as make 6 raised to the k the subject of our assumption, where we would have 5p, and since we have a minus 1 here, therefore if we bring it to the other side, it would be plus 1. So from our assumption, we're saying that 6 raised to the k is equal to 5p plus 1. And since we have 6 raised to the k here, we can just substitute 5p plus 1 in this expression. So from here, we're gonna have 5p plus 1, and notice that it's being multiplied by 6 raised to the 1, which is 6. So I'm gonna put the 6 right here, and then we're gonna have subtract 1. From here, I'm going to expand this, so I'm gonna multiply 6 by what's in the brackets. So 6 times 5p would give us 30p. 6 times 1 would give us 6. So that's plus 6. And then we'll have minus 1. 6 minus 1 would be 5. So I'm going to come down here. So 30p plus 5. And from here, remember that if this is divisible by 5, I can write it as 5 times an integer. So I'm going to factor out 5. So I'm going to have 5, and then in brackets, I'm left with 6p, because 5 into 30 leaves us with 6. And then we'll have the p. And 5 into 5 is 1. Therefore, 6p plus 1 would be an integer. And because 6p plus 1 is an integer, because recall, we already said that p is an integer. So if we have 6p plus 1, it must be an integer as well. So since this is an integer, we can write this in the form of this, 5 times an integer. That means that the expression is divisible by 5, and that would make it true. N is equal to k plus 1, and since it's true for n is equal to 1, n is equal to k, and n is equal to k plus 1, we can make the general conclusion. We can make the general conclusion to say that it's true for every n that is greater than or equal to 1. But here's our final question. We're saying that n times, in brackets, n plus 2 is divisible by 4, where n is equal to 2, 4, 6, and basically positive even integers, right? So the first case we're going to is the base case. So this is where we're showing that it's true for the first case. So notice that this statement is true when n is equal to 2, 4, 6, and onwards. It's true for n is equal to positive even integers. The first positive even integer is 2. Therefore, since that's the first positive integer, that would be our first case, and that's what we would have to use for our base case. So n is equal to 2. So wherever we see n, we're going to substitute for 2. So we're going to have 2, in bracket 2 plus 2. So 2 plus 2 is 4. And then we have 2 times 4. And 2 times 4 is 8. We know that 8 is divisible by 4. Why? Because we can write 8 in terms of 4 times 2. And 2 is an integer. And because 2 is an integer, we're writing 8 as 4 times an integer. 2 is true. It's divisible, therefore it's true. Next, we're moving on to our assumption case. So this is where we're assuming that it's true for n is equal to k. So we're just going to substitute n for k. So we're going to have k in bracket k plus 2. Wherever we say n, we put k. And we're saying that since this is divisible by 4, we can write it as 4 times an integer. And we're making p our integer. And yeah. Also, I'm going to rewrite this. I'm just going to expand this to say k times k squared, k times 2, 2k. Just to have a variation. Next, after doing that, we're moving on to our implication case. And usually with implication case, we know that we're using n is equal to k plus 1. However, remember that we're dealing with positive even integers. And if we're making the assumption that k is even, basically, we're saying that k is even, because we're saying that, n positive even integers and n is equal to k. We're saying that k is a positive even integer. If we were to add 1 to k, that would make 1 plus k plus 1 would be odd. Why? Because if you look at the number system, basically, if you look at integers, we're going to have a even number, then an odd number. Even number, then an odd number. So, for example, 2. What's after 2? 3. 3 is odd. But after 3, we'll have 4, and 4 is even. Therefore, we're not going to have one even number after the other. So, therefore, k plus 1 wouldn't be even. So, in this case, we would have to use n is equal to k plus 2. Because we know that that's even. After we do that, we're just going to substitute for k plus 2. So wherever we say n, we're going to put k plus 2. So we're going to have k plus 2 in brackets k plus 2 plus 2. And from here, we can simplify and say that this is k plus 2. And since we have k plus 2 plus 2, that would give us k plus 4. So remember, with the implication case, we're always trying to find a way to use our assumption right here. So the best thing for us to do right here is for us to basically expand the brackets so we can find our assumption, and eventually we can substitute. Once we see this form right here, we can substitute and put 4p. So that's what we're doing. So we're gonna expand this. We'll have k times k. That would be k squared. K times 4, 4k. 2 times k would give us 2k, and 2 times 4 would give us 8. We'll simplify this expression, and we're going to get k squared. So 4k plus 2k would give us 6k, and that would be plus 8. So from here, remember that we're trying to use our assumption, which is up here. So I'm going to rewrite 6k as, for example, 2k plus 4k. Why? So I didn't realize it at the time, but where I have the k squared plus 6k plus 8 was unnecessary, because all I had to do was to rearrange what I had before with the k squared plus 4k plus 2k plus 8, just to have k squared plus the 2k, so I could just substitute. So I didn't realize it at the time, guys. So since we have k squared plus 2k right there, I can substitute and put 4p. So I'm going to have 4p replacing this expression right here, the k squared plus 2k plus 4k. So 4p plus 4k plus 8. Recall, if a number is divisible by 4, we can write it as 4 times an integer. Therefore, all we're going to do is that we're going to factor out 4 from this expression. So we're going to have 4, and we're going to be left with p plus k plus 2. Where this, let's just make a note up here, where this, the p plus k plus 2 is a member of a set of integers. Why? We know that p is an integer from here. K would be an integer because we literally said that it's an even positive integer, and 2 is an integer. Therefore, this whole expression would be an integer. And since we write it as 4 times an integer, this as 4 times an integer, we basically showed that it's true for the expression is true for n is equal to k plus 2. And since we showed that it's true for n is equal to 2, our first case, n is equal to k, and n is equal to k plus 2, we can make a general conclusion to say that the expression n in bracket n plus 2 is divisible by 4, where n is positive even integers, is true. That's a wrap. Yeah.